January 1941, San Diego, California. The California sun beats down on Consolidated Aircraft's outdoor assembly yard, where America's newest bombers sit half-finished under makeshift canvas covers. Heat waves distort metal parts scattered across the ground. Engines hang from improvised wooden rigs. Charles Sorensen, Ford's 60-year-old production chief, watches skilled craftsmen hand-fitting each component with the methodical precision that European aviation traditions demanded was absolutely necessary for aircraft construction. Every aviation expert knew the truth. Complex bombers required months of careful assembly. Precision aerospace engineering could never be rushed or systematized like simple automobile manufacturing. Aircraft construction was an art form that demanded master craftsmen working at individual stations. That night, in his hotel room, Sorensen sketched something on hotel stationery that would challenge everything the aviation establishment believed about aircraft production. One sketch that would prove American manufacturing could compress the impossible into something the world had never seen before. The morning inspection revealed everything wrong with American aircraft production in 1941. Sorensen moved through Consolidated's sprawling San Diego facility with the methodical eye of a man who had spent 4 decades perfecting assembly line science. Workers hauled heavy bomber sections across uneven ground using ropes and makeshift dollies. Fuselages sat exposed to temperature fluctuations that warped aluminum panels beyond acceptable tolerances. Engine installations required teams of skilled mechanics working for days to hand-fit each power plant, adjusting and readjusting mounting brackets until everything aligned within specifications. The numbers told a devastating story. Consolidated's best production rate averaged 1 B-24 bomber every 3 weeks. Each aircraft demanded hundreds of hours of skilled labor, with master craftsmen moving between workstations like medieval guild artisans. Quality control inspectors examined every rivet, every wire run, every control surface with magnifying glasses and precision measuring tools. The process consumed enormous amounts of skilled labor that America simply did not possess in wartime quantities. Consolidated's chief engineer explained their philosophy with the patient tone of a professor addressing a promising but naive student. Aircraft construction represented the pinnacle of precision manufacturing, he insisted, requiring tolerances measured in thousandths of an inch and assembly techniques passed down through generations of European-trained craftsmen. The Liberator bomber contained over 30,000 individual components, each requiring careful inspection and hand-fitting to ensure structural integrity at 25,000 feet. No shortcuts existed in aerospace engineering. No mass production methods could replicate the meticulous attention to detail that kept air crews alive in combat. The established aviation industry had developed these methods through decades of European influence and hard-learned lessons. British and German aircraft manufacturers operated on craft guild principles, where master mechanics trained apprentices for years before trusting them with critical assembly tasks. Each bomber represented months of careful work by teams who understood that a single improperly installed bolt or incorrectly torqued fastener could cause catastrophic failure in flight. American aircraft companies like Consolidated, Boeing, and Douglas had adopted these proven European approaches because aviation demanded a completely different mindset than automobile manufacturing. Sorensen listened politely, but his engineer's mind was already calculating waste and inefficiency. He watched skilled workers walking hundreds of yards between supply stations and work areas. He observed bottlenecks where partially completed aircraft waited for specialized craftsmen to become available. He noted the complete absence of systematic workflow that could predict completion times or identify production constraints before they caused delays. That evening, in his hotel room at the Grant Hotel in downtown San Diego, Sorensen spread hotel stationery across the small writing desk and began sketching. The concept emerged with startling clarity. Instead of treating the B-24 as a single, impossibly complex machine requiring months of artisanal assembly, he visualized it as a collection of major sub-assemblies that could move through a coordinated production system. His pencil moved rapidly across the paper, breaking the massive bomber into 11 primary sections: nose assembly, cockpit section, bomb bay, wing center section, outer wing panels, engines, landing gear, tail assembly, armament installations, electrical systems, and final inspection. Each major assembly could be further divided into manageable sub-assemblies that individual work teams could complete using specialized tooling and fixtures. The sketch showed these sub-assemblies moving along parallel production lines that would converge at a main assembly area. Workers would remain at fixed stations while aircraft components moved past them on carefully timed schedules. Each station would perform specific, repeatable tasks using precision tooling designed to eliminate hand-fitting and guesswork. Quality control would be built into the process, rather than added as a final inspection step. Sorensen calculated rough timing estimates in the margins of his sketch. If each workstation could complete its assigned tasks within a predetermined cycle time, and if all sub-assemblies could be synchronized to arrive at the main assembly line in the correct sequence, then the entire system could operate with the predictable rhythm of automotive production. The sketch showed bombers moving through final assembly every 63 minutes instead of every 3 weeks. The excitement of the concept kept him awake past midnight, his mind racing through the engineering challenges and solutions. He envisioned massive stamping presses forming aluminum panels to exact specifications, custom-designed jigs and fixtures that would ensure perfect alignment of major components, conveyor systems that could handle the weight and size of bomber assemblies, training programs that could transform unskilled workers into precision manufacturing specialists within weeks instead of years. But as Ford Motor Company committed to the B-24 production contract in the following weeks, the full magnitude of the challenge revealed itself with crushing clarity. Consolidated provided no usable manufacturing blueprints. Instead, Ford engineers received boxes of rough sketches, hand-drawn templates, and incomplete dimensional drawings that had been adequate for small-scale craft production, but were completely inadequate for mass manufacturing. 200 Ford engineers began working in 3 shifts around the clock, 7 days a week, to create the 3-dimensional technical drawings necessary for mass production tooling. They produced 5 miles of detailed engineering drawings daily, documenting 30,000 separate components with the precision required for automated manufacturing equipment. Each drawing specified exact dimensions, materials, tolerances, and assembly procedures that Consolidated's artisan approach had never required. The task grew more overwhelming as Consolidated continued modifying the B-24 design to incorporate combat lessons learned from European air operations. Engineering change orders arrived daily, making 10,000 of the 30,000 drawings obsolete before Ford's tooling engineers could complete their work. Every design modification rippled through hundreds of related components and required extensive redrafting to maintain system compatibility. Sorensen's hotel room sketch had captured the vision. Now Ford's 1,000-member engineering team would spend the next 18 months translating that vision into the most ambitious manufacturing challenge in American industrial history. Ford's tool design group received an assignment that defied every conventional understanding of manufacturing engineering. 1,000 specialized engineers, machinists, and designers began creating custom tooling for an assembly line that had never been attempted in aviation history. Their task demanded precision equipment capable of handling components ranging from delicate electrical assemblies weighing ounces to massive wing sections weighing several tons, all while maintaining tolerances measured in thousandths of an inch. The scale of custom tooling required staggered, even experienced Ford engineers. 1,600 individual machine tools would need to be designed, built, tested, and installed before a single bomber could move down Sorensen's envisioned assembly line. Each machine tool required months of development to ensure it could perform specific manufacturing operations on aluminum aircraft components with automotive-level repeatability. Stamping presses capable of forming complex fuselage panels from flat aluminum sheets. Precision drilling machines that could create perfect hole patterns for thousands of rivets. Broaching equipment designed to cut precise slots and keyways in landing gear components. Grinding machines that could finish machine surfaces to mirror-like smoothness required for aerodynamic efficiency. Beyond the 1,600 major machine tools, 11,000 specialized fixtures, jigs, and assembly aids would position and hold aircraft components during manufacturing and assembly operations. Some of these fixtures towered 60 feet above the factory floor, designed to support entire wing assemblies while workers installed engines, landing gear, and control surfaces. Each fixture represented a custom engineering solution that would eliminate the hand-fitting and adjustment work that slowed traditional aircraft production to a crawl. The engineering team worked in 3 shifts to maintain 24-hour development schedules. Designers created detailed technical drawings during day shifts. Pattern makers built wooden models and templates during evening hours. Night shift machinists rough-machined prototype tooling. That day shift specialists would finish and test the following morning. The cycle repeated 7 days a week as Ford's engineering department transformed Sorensen's hotel room sketch into manufacturing reality. Quality requirements pushed every aspect of tooling design beyond conventional automotive standards. Aircraft components demanded precision that automotive parts rarely required. Engine mounting brackets needed to be machined within 0.02 of an inch to ensure proper alignment and prevent vibration failures. Wing attachment fittings required surface finishes smooth enough to prevent stress concentration points that could cause catastrophic structural failures. Control surface hinges demanded tolerances so tight that traditional measuring instruments were inadequate for inspection purposes. Albert Kahn received the architectural challenge of housing this unprecedented manufacturing operation. The renowned industrial architect had designed countless automotive facilities for Ford and other manufacturers, but Willow Run demanded innovations that pushed beyond every previous factory construction project. The building would require 3.5 million square feet of enclosed manufacturing space, making it the largest single-story factory structure ever attempted in the United States. Kahn's design team calculated the structural requirements for an aircraft assembly line extending over 1 mile in length. The building would need clear spans wide enough to accommodate bomber wingspans of 110 feet, while providing overhead crane coverage for moving major assemblies. Column spacing would allow aircraft to move through the facility without obstruction while supporting roof loads from massive overhead material handling equipment. The most innovative aspect of Kahn's design addressed the geometric constraints of Sorensen's assembly line concept. A straight mile-long building would require more land area than available at the Willow Run site. Kahn solved this challenge by incorporating 4 large turntables positioned 2/3 along the assembly line route. These turntables would rotate completed aircraft through 90-degree turns, allowing the assembly line to fold back on itself in a distinctive L-shaped configuration that fit within the available property boundaries. Each turntable represented a precision engineering challenge that aircraft manufacturers had never attempted. The rotating platforms would need to support fully loaded B-24 bombers weighing over 36,000 pounds, while maintaining perfect alignment with incoming and outgoing conveyor systems. Electric motors and gear reduction systems would rotate aircraft through precise 90-degree increments without disturbing delicate control cable adjustments or instrument calibrations completed at upstream assembly stations. Construction crews broke ground in April 1940 and worked around the clock to complete the massive structure within 18 months. Steel framework rose from specially prepared foundations designed to support the concentrated loads from overhead cranes and material handling equipment. The building's distinctive sawtooth roof design provided natural lighting for precision assembly work while accommodating ventilation systems that would remove fumes from welding and painting operations. Concrete floors throughout the facility were specified to tolerances typically reserved for precision machine tool installations. Any deviation from perfect flatness would cause alignment problems as aircraft assemblies moved along the mile-long conveyor system. Survey crews used precision optical instruments to ensure floor elevations remained within 1/8 inch across the entire building length. Electrical systems required innovation matching the building's unprecedented scale. Power distribution networks would supply electricity to 1,600 individual machine tools while providing lighting adequate for precision assembly work across 3.5 million square feet of factory space. Emergency systems would ensure uninterrupted production even during utility power outages that could idle thousands of workers and disrupt carefully timed assembly sequences. The building's completion in late 1941 represented only the beginning of the installation challenge. 1,600 machine tools and 11,000 fixtures would need to be positioned, aligned, tested, and integrated into a coordinated manufacturing system capable of producing one bomber every 63 minutes. Sorensen's vision was becoming the largest, most complex manufacturing facility ever constructed, ready to prove whether American industrial methods could revolutionize aircraft production or collapse under the weight of unprecedented complexity. The massive Willow Run facility came alive in stages throughout 1942 as Sorensen's methodical approach to bomber assembly revealed itself through systematic implementation. His vision required breaking the B-24 Liberator into 11 major assemblies that could move through parallel production streams before converging at the main assembly line. The nose section, cockpit assembly, bomb bay structure, wing center section, outer wing panels, engine installations, landing gear systems, tail assembly, armament packages, electrical networks, and final inspection stations each demanded specialized workflows and custom tooling. Sorensen further divided these 11 major assemblies into 69 distinct sub-assemblies, creating a manufacturing hierarchy that transformed the impossibly complex bomber into manageable production units. Each sub-assembly could be completed by specialized work teams using dedicated tooling and fixtures designed for specific repetitive tasks. Wing ribs moved through precision forming operations on custom stamping equipment. Fuselage frames followed parallel assembly sequences using specially designed jigs that ensured perfect alignment and dimensional accuracy. Control surfaces received their own dedicated production lines where workers installed actuators, cables, and surface coverings using standardized procedures that eliminated guesswork and hand-fitting. The workforce transformation began gradually as Ford's training programs converted inexperienced workers into precision aircraft assemblers within weeks instead of the years traditionally required by aviation craft guild methods. Training supervisors developed specialized instruction programs for each workstation, teaching specific skills required for individual assembly operations. Workers learned to operate precision measuring instruments, read complex technical drawings, and perform repetitive tasks to tolerances measured in thousandths of an inch. Employment levels climbed steadily throughout 1942 as production requirements expanded. The facility employed 12,000 workers during initial startup operations. By summer, employment reached 28,000 as additional assembly lines came online. Peak employment of 42,000 workers was achieved by early 1943, making Willow Run the largest single manufacturing employer in Michigan and one of the largest industrial facilities in the world. The wartime draft created an unprecedented labor shortage that forced fundamental changes in American manufacturing demographics. As men departed for military service, thousands of women entered industrial work for the first time in their lives. Former housewives, teachers, and retail clerks learned to operate precision drilling equipment, perform complex riveting operations, and conduct quality control inspections on critical aircraft components. Training programs taught welding techniques, blueprint reading, and mechanical assembly skills to women who had never worked with metal or precision tools. Roswell Monroe exemplified the remarkable transformation taking place across American industry. A young widow from Kentucky, Monroe arrived at Willow Run seeking steady employment to support her family while her husband served in the Pacific Theater. Training supervisors assigned her to riveting operations on fuselage assembly lines, where she learned to install thousands of aluminum rivets with pneumatic tools that demanded precise positioning and consistent pressure application. Her competence and reliability in precision assembly work made her a natural candidate for training. Other women workers as production demands expanded. Monroe and thousands like her mastered manufacturing skills that aviation industry experts had insisted required years of specialized training under master craftsmen. Within months of beginning work, these women workers were producing aircraft components with quality levels that met or exceeded traditional aviation industry standards. Their success demonstrated that systematic training programs and properly designed tooling could enable inexperienced workers to achieve precision manufacturing results previously reserved for master artisans. The assembly line began producing complete aircraft as individual workstations synchronized their operations with the overall production rhythm. Each workstation performed specific tasks within predetermined cycle times that allowed aircraft assemblies to move through the system at predictable intervals. Workers remained at fixed positions while bomber components moved past them on carefully timed conveyor systems. This approach eliminated the walking, waiting, and searching that consumed enormous amounts of time in traditional aircraft manufacturing methods. Quality control integrated into each workstation rather than being concentrated in final inspection areas. Workers used precision measuring instruments to verify dimensional accuracy before passing components to the next assembly station. This systematic approach identified and corrected problems immediately rather than allowing defects to accumulate through multiple assembly stages before discovery during final inspection. On October 1, 1942, the first complete B-24 rolled off Willow Run's mile-long assembly line after months of testing, adjustment, and refinement of Sorensen's manufacturing system. The aircraft was christened the Spirit of Ypsilanti in recognition of the local community that had embraced the massive industrial project. Flight tests confirmed that the bomber met all military specifications for performance, structural integrity, and operational reliability, despite being manufactured using mass production methods that aviation experts had declared impossible for complex aircraft construction. The successful completion of the first bomber validated Sorensen's fundamental insight that precision manufacturing depended more on systematic processes and specialized tooling than on individual craftsmen's skills. The Spirit of Ypsilanti proved that American industrial methods could produce aircraft with quality levels equivalent to traditional European craft approaches while achieving production rates that were orders of magnitude faster than anything the aviation industry had previously accomplished. Production rates increased steadily as workers gained experience with their specialized tasks and as manufacturing processes were refined to eliminate bottlenecks and inefficiencies. The systematic approach allowed supervisors to identify constraints in the production system and implement targeted improvements that increased overall throughput without compromising quality standards. Sorensen's vision of one bomber every 63 minutes remained the goal, but achieving that target would require overcoming challenges that threatened to derail the entire program before it could reach full production capability. The dual authority structure that governed B-24 production created cascading problems that threatened to destroy Sorensen's manufacturing revolution. Consolidated Aircraft retained significant control over design specifications and engineering changes, while Ford assumed responsibility for mass production implementation. This arrangement seemed logical to military procurement officials who wanted to preserve Consolidated's expertise while leveraging Ford's manufacturing capabilities, but it created operational chaos that neither company had anticipated. Engineering change orders arrived at Willow Run with devastating frequency as Consolidated incorporated combat feedback from European and Pacific theater operations. Modifications to defensive armament configurations required extensive retooling of gun mount installations and ammunition storage systems. Changes to fuel system layouts demanded new wing tank designs and fuel line routing that affected dozens of related components. Engine cooling modifications altered cowling shapes and air intake geometries, forcing Ford's tooling engineers to redesign expensive stamping dies and assembly fixtures. Each design change rippled through Ford's carefully orchestrated production system like seismic shocks. Components that had moved smoothly through assembly sequences suddenly required hand-fitting and modification work that bottlenecked entire production lines. Workers trained for specific repetitive tasks found themselves struggling with one-off modifications that demanded traditional craft skills they had never developed. Quality control procedures designed for standardized components became inadequate for evaluating modified parts that fell outside established specifications. The modification cycle consumed enormous engineering resources as Ford's technical teams worked around the clock to translate Consolidated's design changes into updated manufacturing procedures. New technical drawings, revised tooling specifications, and modified work instructions had to be created, reviewed, and distributed to 42,000 workers across 3 shifts. The 5-mile daily output of engineering drawings that had seemed impressive during initial development became grossly inadequate for managing constant design evolution. Production scheduling collapsed under the weight of unpredictable change orders. Assembly lines designed for synchronized 63-minute cycle times experienced delays that accumulated throughout the mile-long facility. Aircraft assemblies arrived at final stations with missing components that were still being redesigned at upstream suppliers. Workers waited for modified parts while completed assemblies occupied assembly line positions needed for incoming production. The systematic flow that had validated Sorensen's vision deteriorated into the stop-and-start chaos that characterized traditional aircraft manufacturing. Quality problems emerged as workers struggled to implement modifications using tooling and procedures designed for different component configurations. Rivet patterns that had been perfect for original designs created stress concentrations when applied to modified structural arrangements. Electrical installations that met specifications for initial wire routing configurations failed inspection when adapted to revised layouts. Control surface adjustments that had been standardized for original aerodynamic configurations required extensive hand tuning when applied to modified wing and tail designs. Congressional investigators arrived at Willow Run in spring 1943 to examine production delays that were affecting military aircraft delivery schedules. Their investigation revealed the fundamental management problem that was crippling Ford's manufacturing system. Divided authority between Consolidated and Ford created decision-making delays, communication failures, and responsibility conflicts that prevented effective problem resolution. Neither company could make unilateral decisions about production issues that affected both design specifications and manufacturing processes. The investigators documented specific examples of the dual authority dysfunction. When Ford engineers identified manufacturing problems with Consolidated's designs, resolution required lengthy coordination between multiple engineering teams, military representatives, and corporate management structures. Simple decisions that should have taken hours stretched into weeks as responsibility ping-ponged between organizations with different priorities and operating procedures. Critical path. Bottlenecks that could have been resolved immediately under single company control became major production delays under the divided authority structure. Aviation industry critics seized upon Willow Run's struggles as validation of their long-standing skepticism about automotive manufacturing methods applied to aircraft construction. Technical journals published detailed analyses of Ford's quality problems, highlighting examples of manufacturing defects that traditional craft approaches would have prevented. Industry conferences featured presentations comparing Willow Run's troubled production rates with the steady, reliable output of established aircraft manufacturers using proven European-influenced methods. The mile-long mistake became shorthand for the failure of American industrial ambition when applied to precision manufacturing challenges that demanded traditional craft expertise. Editorial writers and industry analysts argued that Sorensen's vision had been fundamentally flawed from the beginning. Complex aircraft construction required the accumulated knowledge and careful attention to detail that only master craftsmen could provide. Mass production methods that worked adequately for automobiles were inherently inadequate for aerospace applications, where component failures could cause catastrophic consequences. Production statistics supported the critics' arguments. Willow Run's output during the first half of 1943 fell far short of projected targets. Monthly production rates fluctuated wildly as engineering changes disrupted carefully planned assembly sequences. Quality rejection rates exceeded acceptable levels as modified components failed to meet military specifications. The facility that was supposed to revolutionize aircraft manufacturing was producing fewer bombers per month than several smaller facilities using traditional manufacturing approaches. Morale among Willow Run's workforce declined as production problems mounted and criticism intensified. Workers who had taken pride in mastering precision manufacturing skills found themselves struggling with constant modifications that made their training obsolete. Supervisors faced impossible scheduling challenges as design changes invalidated carefully developed production plans. Engineers who had worked around the clock to create Ford's manufacturing system watched their innovations being undermined by forces beyond their control. The dream of mass-produced aircraft that had inspired Sorensen's hotel room sketch seemed to be dying under the weight of operational reality. European aviation experts who had predicted that American industrial methods could never master aircraft manufacturing precision appeared to have been correct. The systematic approach that had transformed automobile production looked inadequate for the complex engineering challenges that aviation demanded. Willow Run stood as a monument to failed American industrial ambition, validating every skeptic who had argued that some manufacturing challenges simply could not be systematized or accelerated beyond traditional craft limitations. The transformation began when military officials finally addressed the fundamental management problem that had crippled Willow Run's potential. In late 1943, a single plant manager received complete operational control over the entire B-24 production program. The divided authority structure that had created endless delays and coordination failures was eliminated, replaced by unified decision-making that could respond immediately to production challenges without lengthy consultation processes between competing organizations. The new management structure empowered Ford engineers to implement design modifications directly rather than waiting for approval from Consolidated's engineering teams. When production bottlenecks emerged, plant supervisors could authorize immediate tooling changes, worker reassignments, and process modifications without navigating complex approval hierarchies. Quality problems that had previously required weeks of intercompany coordination could be resolved within hours by teams with clear authority and responsibility for results. Engineering change orders that had disrupted production schedules were consolidated and managed through systematic implementation procedures that minimized their impact on assembly line operations. Instead of implementing modifications as they arrived from Consolidated, Ford's engineering teams batched changes into periodic updates that allowed production lines to operate with consistent configurations for extended periods. This approach eliminated the constant retooling and worker retraining that had destroyed production rhythm during the facility's troubled startup period. The systematic flow that Sorensen had envisioned in his hotel room sketch finally began operating as designed. Aircraft assemblies moved through the mile-long facility with the predictable timing that mass production methods required. Workers at each station completed their specialized tasks within predetermined cycle times that synchronized with the overall production rhythm. Components arrived at assembly points exactly when needed, eliminating the waiting and searching that had characterized traditional aircraft manufacturing approaches. Quality control procedures that had been designed for standardized production finally functioned effectively once design modifications were managed systematically. Workers used precision measuring instruments to verify component specifications at each assembly station, identifying and correcting problems immediately rather than allowing defects to accumulate through multiple production stages. Rejection rates dropped to levels that met military specifications while maintaining production speeds that exceeded anything the aviation industry had previously achieved. By early 1944, Willow Run was demonstrating the manufacturing capability that had been promised in Sorensen's original vision. Complete B-24 Liberators rolled off the final assembly line every 63 minutes, 24 hours a day, 7 days a week. The systematic approach that aviation experts had declared impossible for complex aircraft construction was producing bombers with quality levels equivalent to traditional craft methods while achieving production rates that were orders of magnitude faster. The numbers validated every aspect of Sorensen's revolutionary approach to aircraft manufacturing. During April 1944, employees working 2 9-hour shifts, 6 days a week, produced 453 complete aircraft in 468 working hours. This production rate exceeded the monthly output of entire aircraft manufacturing complexes using traditional European-influenced methods. Individual workstations completed their assigned tasks with precision that eliminated the hand-fitting and adjustment work that slowed conventional assembly approaches. Peak monthly production reached 428 B-24 bombers, a rate that demonstrated the scalability of mass production methods when applied to precision manufacturing challenges. Each aircraft contained over 30,000 individual components, manufactured to tolerances measured in thousandths of an inch, assembled by workers who had learned precision manufacturing skills within weeks rather than the years traditionally required for aviation craft training. The workforce that had been dismissed as inadequately skilled for aircraft construction was producing bombers that met all military specifications for structural integrity, operational reliability, and combat effectiveness. Women workers who had never touched precision manufacturing equipment were completing complex assembly operations with quality levels that equaled or exceeded the work of master craftsmen trained under traditional European guild systems. The systematic training programs and specialized tooling that enabled this transformation proved that manufacturing precision depended more on process design than individual skill development. Production continued at peak rates through 1944 and into 1945 until military victory in Europe reduced demand for strategic bombers. On June 28, 1945, the final B-24 rolled off Willow Run's assembly line after the facility had manufactured 8,685 complete aircraft. Ford had produced 6,972 of the 18,482 total B-24 Liberators manufactured during the war, representing nearly 40% of all bombers in this class. The contrast with modern aircraft manufacturing highlighted the remarkable achievement that Willow Run represented. Contemporary F-35 fighter aircraft required 23 years from initial development to full-rate production approval, a timeline longer than the entire span from the Wright brothers' first flight to Willow Run's peak production. Each modern F-35 demanded 41,500 hours of labor compared to the streamlined processes that had enabled Willow Run's 63-minute production cycle. The transformation from Willow Run's initial concept to final production victory demonstrated that complex electronics, extensive certification requirements, and supply chain complications that characterize modern aircraft development were not fundamental barriers to efficient manufacturing. The streamlined wartime system had eliminated many of the regulatory and procedural obstacles that extended contemporary development timelines without improving actual manufacturing outcomes. Sorensen's hotel room sketch had accomplished more than revolutionizing bomber production. Willow Run proved that American manufacturing ingenuity could compress impossibly complex manufacturing challenges into predictable, repeatable processes that outproduced the world. The systematic approach that transformed precision aircraft construction from craft guild methods to mass production principles established manufacturing capabilities that would define American industrial leadership for generations. European aviation experts who had insisted that complex aircraft required traditional artisanal approaches had been proven fundamentally wrong by workers who had never seen an aircraft before, learning to build them faster and better than anyone had thought possible.